You ever think about what's running just out of sight, all around us? There's this massive, hidden network of industrial piping. It's basically the circulatory system of our entire economy. And keeping it safe, well, that's a seriously high-stakes job. Today, we're going to pull back the curtain and see exactly how it's done.
Imagine a refinery or a chemical plant as like a living thing. Its arteries aren't carrying blood, they're carrying this volatile mix of materials that are absolutely essential, but also a lot of the time extremely hazardous. And it's all flowing 24/7.
And we're not talking about a few feet of pipe here. This is thousands upon thousands of miles, all operating under constant, unbelievable stress. The pressures, the temperatures, they are just extreme, pushing that steel to its absolute limit every second of every day.
So what's the one thing standing between a plant just humming along and, well, a potential catastrophe? The answer is an incredibly rigorous systematic inspection process. And it's all guided by this comprehensive standard from the American Petroleum Institute known as API 574.
Okay, so why is this so critical? I mean, really, what are we talking about here? The stakes involved in making sure these pipes stay in one piece are just incredibly high.
Because a single leak is never just a drip. It can kick off this whole domino effect of disasters, from fires and terrible environmental damage to sudden shutdowns that can cause just massive economic losses. The consequences are huge.
And check out this quote from the API document itself. It is honestly pretty chilling. It shows just how quickly things can go wrong. A small, what looks like a manageable leak can just erupt into a massive, uncontrolled disaster in the blink of an eye. And that right there is why having a systematic, by-the-book approach is absolutely non-negotiable.
So where does an inspector even begin with all this? Well, it all starts with the first line of defense, a super detailed visual check. Let's step into their boots for a minute and see what they're actually looking for. The whole process often kicks off with what they call a walk-down. An experienced inspector literally walks the lines, using their trained eyes to spot those first little telltale signs of a problem. It's step one, but it can tell you a surprising amount about the health of the entire system.
Now this is where it gets really fascinating, because you see the hidden complexity in what looks like a simple task. So you see a leak at a flange, you think, oh, just tighten the bolts, right? Whoa, not so fast. It is a super delicate balancing act. As you can see here, you tighten one bolt too much, and you could actually loosen the one right next to it. Or even worse, you could warp the entire flange.
Another huge thing they're looking for is misalignment. If a pipe isn't sitting right, it puts this enormous stress across the whole system. And inspectors, they're trained to spot these clues, from something really obvious, like a pipe that's physically slipped off its support, to something way more subtle, like finding out a connected pump has needed a ton of repairs lately.
And then there's the silent killer of pipes, corrosion. It is the relentless enemy, and it absolutely loves to hide in these little spots where moisture gets trapped. This is the real detective work of an inspection, knowing exactly which dark corners to check for trouble before it gets a real foothold.
But, visual checks can only take you so far. To find the really dangerous damage, the problems that are lurking inside the pipe wall itself, inspectors need to be able to see through solid steel. And this is where we get into some really high-tech stuff.
I mean, think about it. How on earth do you check for corrosion at a spot where the pipe is resting directly on a support beam? It's completely hidden. You can't see it. But it could be the single weakest link in the entire line.
This is where something called non-destructive examination, or NDE, comes into play. You can think of it as a high-tech toolkit for seeing the invisible. And as you can see from this table, inspectors have a bunch of options. The real key is knowing which tool to use for which job, because every single one has its own strengths and its own limitations.
The most common method by far is ultrasonic examination, or UT. It works kind of like a bad sonar. A device sends a high-frequency sound wave through the steel, and by measuring the exact time it takes for that echo to bounce back, it can calculate the wall thickness with incredible accuracy.
But these tools aren't magic. Here's a fascinating and frankly dangerous pitfall called doubling. When a pipe wall gets super thin, the instrument can actually misread the echo and report a thickness that is literally double what it really is. Can you imagine the danger of thinking a pipe wall is twice as thick as it actually is? It's a perfect example of why the skill of the human operator is still so critical.
Another really powerful tool is radiography, which is basically an X-ray for pipes. It gives you a direct picture of what's happening on the inside. This slide shows a classic case of corrosion in what's called a dead leg. That's a section of pipe where the fluid doesn't really flow. It just sits there, stagnant, and it creates the absolute perfect breeding ground for some really aggressive corrosion.
So the inspector has all this data: visual clues, ultrasonic readings, x-rays, the whole shebang. Now comes the moment of truth, making sense of it all to answer one simple but absolutely critical question: how thin is too thin? And that decision isn't just a guess. It's a precise three-step process. First, they calculate the thickness needed just to hold the pressure. Second, they figure out the thickness needed to support the pipe's own weight without collapsing. And here's the crucial part: the final minimum thickness is the larger of those two numbers. It is the ultimate better safe than sorry engineering principle right there in action. That pressure design thickness, that's pure engineering. It's a calculation, a formula that balances the pressure inside the pipe, how wide the pipe is, and the known strength of the steel it's made from. It's all about making sure that pipe can handle the force pushing out from the inside.
This slide breaks that down perfectly. On one side, you have the pressure requirement. On the other, you have the structural one. For example, a really big pipe with almost no pressure inside might not need to be thick to hold the fluid, but it would totally sag and collapse under its own weight if it wasn't thick enough. That's why that structural minimum is just as important.
And to put a real number on it, let's take a common 14-inch pipe, one designed for 600 psi. After you run all the formulas, the absolute rock-bottom minimum required thickness comes out to 0.208 inches. If an inspector measures anything less than that, well, a decision has to be made, and fast.
So we've got the visual checks, we've got the advanced data, and we've got the hard calculations. Now we're at the final step, bringing it all together to make the call.
Because in the end, this is the key takeaway from all of this. Pipe inspection isn't just about ticking boxes on a checklist. It's this sophisticated judgment call that blends hard data from advanced tools, solid engineering principles, and, this is the most important part, the invaluable experience of the inspector. It is all about the essential human element in this super high-tech world.
And it kind of leaves you with this thought, doesn't it? This is just one tiny piece of the puzzle. What other complex, invisible risks are being carefully managed by skilled professionals all around us every single day, just to keep our world running?